Okay, hi everybody. Today we are going to start chapter 12 on the topic of fluid mechanics. So this should be a really fun chapter, really relevant to basically all fields of science and also engineering, and also really relevant to your everyday life. This is something you deal with every day, and so this chapter will hopefully help us to better understand the world around us. And this picture is a fun one. This is looking at the water coming out of the bottom of the Hoover Dam. Um, and you can see we've got thousands and thousands of tons of water, thousands of gallons of water coming out from these four different spouts, and they're traveling, hundreds of feet before hitting the water. So based just on that distance, and this water is traveling in projectile motion, we could basically figure out how fast that water is coming out from those spouts, and it's coming out fast. So we have thousands of tons of water coming out really fast. That's a lot of kinetic energy that this water has right now. Where does that energy come from? Okay, the water on this other side of the dam is not moving, right? It's just water under high pressure. Coming out of the spout, we have a lot of kinetic energy. So where is that energy coming from? So we're going to try to understand that in this chapter. Before we do so, let's just make a few definitions. First, we're going to define density. Of course, density is a property of any material, and so we're going to define our mass density to be the mass per unit volume. Right? So this is m over v, where the symbol we're using is the Greek letter rho. All right, so it looks kind of like a p, but it's a little bit more curly. So this is the Greek letter rho, and that's the symbol we're going to use for density. And to calculate density, again, just take the mass in kilograms and divide it by the volume. So of course the SI unit therefore becomes a kilogram per cubic meter. And so there's no given name for the unit of density. It's just kilogram per cubic meter. And we're basically going to limit our discussion to homogeneous materials that have the same density throughout the material. So something like aluminum or water, oil, or something like that. Nothing that has a varying density. And of course, if you look at a steel wrench, you look at a steel nail. These are two objects made out of the same material. They both have the same density, even though they have different volume and different mass. All right, so you may be able to use density to actually identify a material. And we can look at some common materials. First, we have one gas on this list, which is air. Air at 1 atmosphere of pressure, 20 degrees Celsius temperature. The density is about 1 kilogram per cubic meter. So you can picture a cubic meter, and it's a pretty big, about the size of your span of your arms, volume, a cube that large. And within that cube is about 1 kilogram of air, right? So that's about the density of air. If we look at now solids, the density is much larger, right? So looking at ice, water, metals, right? It's more like 1,000 kilograms per cubic meter. And we can see again that water is actually more dense than ice. Liquid water is more dense than solid ice. Blood is a little bit more dense than water, for example. So when you're solving problems in a fluid mechanics chapter, especially when you're using an online homework system like Mastering Physics, you want to actually look up the density of the material they list in the problem. So the density of salt water is a little bit different than the density of water, which is a little bit different than the density of blood. So make sure you look up the actual number in a table before you solve that problem. Now looking at things like aluminum, lead, and gold, we're now getting to things that are more like 10,000 kilograms per cubic meter of density. So let's do a quick clicker question. This is one you can do just in your head. So we have two different spheres. The sphere on the left has mass of m. The sphere on the right has double the mass of 2m. The sphere on the left has a radius of r. The sphere on the right has a radius of 2r. So even though they're the same color, they're not necessarily the same material. Right? We just know that this one has double the mass, this one has double the radius. So the question is, do these two spheres have the same density? Do they have twice the density, half the density, a quarter, an eighth the density? So take a moment, pause the video, think about this problem, and then on the next slide we'll go through the solution. Okay, so it turns out the right answer here is D, 1/4 the density. And this is, I think, a problem that I commonly see students get wrong, especially if they just think about it relatively quickly. Because you're doubling the mass, doubling the radius, it seems like you should be keeping the density the same. But we have to remember that volume depends on radius cubed, right? So that's where this problem gets a little bit more tricky. So the volume of a sphere is given by 4/3 pi r cubed. So if the radius of, I'll call the small ball, small sphere, object 1, the big sphere, object 2, the radius of the small ball is just equal to big R, where the radius of the larger ball is equal to 2 times r, or 2 times the radius of the small ball. The volume of the small ball is just 4/3 pi r1 cubed. The volume of the big ball is 4/3 pi times r2 cubed, where r2 is equal to 2 times r1. So I'm going to plug 2 times r1. Now I have to cube that 2. Right? So I end up getting 8 times 4/3 pi r1 cubed, or 8 times the volume of ball 1. So going from ball 1 to ball 2, I'm doubling the radius, but I'm making the volume 8 times bigger. Okay. So now if I calculate my density for ball 1, it's just the mass of ball 1 divided by V1, the volume of ball 1. But the density of ball 2 is now 2 times the mass divided by the volume of ball 2. But the volume of ball 2 is 8 times the volume of ball 1, so I get 1/4 m over V1, or 1/4 the volume, 1/4 the density of ball 1. Right? So the correct answer here is 1/4 the density. So this is just, if you didn't get it right, it's just a reminder to you that you should always think about volume being different than radius, right? In general, things are going to depend on a radius cubed when talking about volumes. Okay, we talked about density. Now let's also talk about pressure. Okay, so this is the first time in the class we've really talked about pressure. Pressure we are going to define to be the force per unit area. So basically, if you're applying a force over some area, we're just going to divide force by that area. So I've got one box here. If I put the box flat on the table, the force of gravity acting on it is 100 newtons, and therefore the force of that box on the ground is 100 newtons. If I turn that box on its side, the force of gravity acting on it is still 100 newtons, so the force of that box on the ground is still 100 newtons. But when I turn it on its side, I'm making the area about 10 times smaller, and so I have the same force but a smaller area, so the pressure is going to be much larger for the box on its side. Right? So the pressure is going to be bigger. So you have the same force, different area, you end up with a different pressure. All right, so it's the same thing as why does a nail work, right? If you bang on a wooden block, you're not going to push that wooden block into the wall. But if you bang on a nail, you can push that nail into the wall. You're applying the same force over a much smaller area, you get more pressure. Okay. To understand pressure a little bit better, especially for liquids, I'm going to use this simulation. We're going to talk a lot about the pressure in different liquids. How does that pressure vary as you go deeper in a liquid? How does it vary within water flowing through a moving through a pipe, things like that. So to understand pressure for fluids, it really, really helps to think about the actual molecular level, thinking about all the actual molecules bouncing around inside some container for a liquid or a gas. So to do that, I'm going to go to this link, one of these nice PhET simulations, and I encourage you to also do this and play around a little bit. So here we just have a box, some kind of container, and I have a nice air pump. So I'm going to push on the pump, and every time I do, I'm going to put some molecules of air into this box. And I can see these molecules are going to bounce around and just in a second or two just kind of fill up the entire area. And I can see that these molecules are bouncing around, they're knocking off each other, and they're knocking off the wall. Okay, and I can also see on this pressure gauge that it's telling me there's 20 atmospheres of pressure on this box. Okay, so what is that telling me? Pressure is force over area, so that's telling me that somehow these molecules bouncing around are applying some force over any given area. Right, so if I just pick one side of the box, I can see that every second there's some number of molecules that are hitting that side of the box. Right? And that's where this pressure is coming from. It's coming from these collisions of these molecules as they're flying around. These molecules are hitting the wall, they're applying a force on the wall's applying a force back on the molecules, right? And if we sum up all those different collisions for, in this case, it's hundreds of molecules, but in a real liquid or gas, it's going to be billions and billions of molecules. If we sum up all those tiny little forces from all of those collisions, that's what the pressure is, right? So the pressure is perpendicular to any surface, right? So on this surface, the molecules are applying a force in this direction, right, pushing on the wall in that direction. But on the top of the box, the molecules are hitting the top of the box in this direction, so they're applying the pressure in that direction, perpendicular to the surface. On this side of the wall, they're applying the force in this direction, perpendicular to the surface. And on this surface, they're applying the force in this direction, perpendicular to the surface. Right? And if I was to submerge something inside this box, just put a sheet of paper inside here or something, it doesn't matter what angle I put that sheet of paper in, there's going to be molecules hitting one side of the paper and the other side of the paper and applying some pressure, some force per unit area. So it really helps to think about this kind of on the molecular level and think about all these little collisions, putting all these little tiny impulses on the wall, right? Summing up all of those forces is where you get pressure, right? In this case, it's 20 atmospheres, and you could, increase the temperature of this. Let me see, how do I do that? Oh, here, I can add some heat down here. Okay, I can add some heat, and you can see in doing so, I'm making those molecules move faster and faster. I'm increasing the kinetic energy of the molecules. I now have faster moving molecules that are hitting the wall, and therefore there's a bigger impulse on those molecules, and so there's a bigger force of those molecules on the wall, and I've increased the pressure inside this volume to 40 atmospheres. It was at 20 atmospheres before. Right, so this can really be helpful for us in trying to understand pressure in fluids. Okay, so moving back to the slides. Pressure on a fluid. So a fluid exerts a force perpendicular to any surface in contact with it. So this could be the wall of the container, or could be something immersed in the fluid. If I consider one tiny surface area, just my differential of the area, dA, the pressure at that point is just the force over the area. And here I have an F symbol with this little upside down T. All right, the upside down T means perpendicular, right, at a right angle, a 90-degree angle. So the force is always at 90 degrees to the surface. Okay, and that's where we're going to define pressure. Pressure is force divided by area. Okay, and pressure has a SI unit, of course. The SI unit of pressure is called the Pascal, so we give it a special name. 1 Pascal, or 1 capital P lowercase a, is equal to 1 Newton per meter squared. Right? Force is newtons, area, the SI unit is meter squared. So a Pascal is defined to be a Newton per meter squared. Okay. And just thinking about pressure, and again, keep that that simulation of all those molecules bouncing around in your head. If I was to submerge just a little sheet of plastic into that liquid, there would be molecules hitting both sides of that piece of plastic. Right? In any given period of time, it's going to be millions and millions of collisions of those molecules. So both sides of that piece of plastic are going to have some pressure on them. There's going to be some force per unit area. Right? But it's going to happen on both sides of that piece of plastic. So there's no net force acting on that piece of plastic. That piece of plastic is not going to accelerate. But there is a force because there is pressure on both sides of that piece of plastic. There are molecules hitting both sides of it. Okay. If I was to change the orientation of that piece of plastic, I wouldn't change the pressure because there's still molecules hitting both sides of that piece of plastic. And in fact, even if I change the orientation and increase the size of the area of my piece of plastic, so if I double the area, right, if I double the area, I'm doubling the amount of area for molecules to hit that piece of plastic. So there's going to be more force. If I double the area, I'm actually going to double the force acting on that side of the piece of plastic. Right? So if this is 2 times the force, this is just 1 force. Right? So I'm doubling the force, I'm doubling the area, but I haven't changed the pressure, right? Because pressure is force divided by area. So if I double the area, I double the force also, the pressure stays the same. Okay. And pressure is just a scalar quantity, right? So it's not a vector. The force direction is always going to be perpendicular to the surface, but pressure is just a number when we use it in calculations. Just a quick comment. We're going to spend a lot of time talking about liquids in this book. For the majority of our discussion, it's important that we remember that the liquids that we're talking about, things like water, are incompressible fluids, right? It's going to be really important that water be incompressible. That if you have a pipe that's sealed on both ends, and say you completely fill this water and then you try to push another gallon of water into that pipe, you can't do it. Or if you have a pipe that's open on both ends, you put a gallon of water on one side of the pipe, a gallon of water has to come out the other side of the pipe. You can't squeeze any more in there. It's not compressible. Right? This is not the same as a gas. A gas can change volume where a liquid cannot. So if you have a pipe filled with gas, you can always push more gas into there, increase the pressure of the gas everywhere. But change the, or gas can change volume if you put it in a different container. Liquids cannot, right? Liquids we can think of them as being nearly incompressible. For the first half of this chapter, we're going to talk about static liquids, right? Static meaning just liquids at rest. And then the second half of the chapter, we're going to talk about moving liquids. All right, so this is more fluid dynamics, where we're generally going to talk about liquids moving through a closed system where you have a completely filled pipe. And again, you put a gallon of water in one side, a gallon has to come out the other side. So now that we've defined pressure, let's talk a little bit more about units. It turns out pressure has a lot of complicated units used in different fields. So we really have to make sure we understand how to convert all of these, because if you're an engineer, if you're in medical fields, if you're in atmospheric science, if you're a meteorologist, all these different fields use different units for pressure. So let's make sure we understand those. So as we talked about already, the SI unit, right, is the Pascal, which is 1 Newton per meter squared. But then if you go to a different field, for example, if you look at a weather report and you look at the pressure of air, right, we have 900 over here, we have 1,000 over here, right, we see these pressure changes given by the yellow lines on this weather map. In the field of meteorology, people also often use things like millibar or bar, right? So a bar is 10 to the 5th pascals, a millibar is 100 pascals. Right, so that field tends to use different units, okay? And so you can convert between bar and millibar and pascals using these conversion factors. In the US, it's really common to use PSI, right? Pounds per square inch. So if you look at a tire pressure gauge or a bike pump, that's typically going to be in PSI. Right? This is how many pounds of force are affecting every square inch of a tire, for example. So 1 psi is equivalent to 6,895 pascals. In medicine, if you go get your blood pressure checked and you get your systolic and diastolic pressure measured, you may be able to see it, maybe not. The unit here is mmHg. This stands for millimeters of mercury. Right? So 1 millimeter of mercury is also kind of given the name 1 torr, and this is equivalent to 133 pascals. Okay, so in medicine, they use a different unit, okay, which is millimeters of mercury. And finally, since we have atmosphere and we're used to 1 atmosphere of pressure, it's also common to use 1 atmospheric pressure as being a good unit, right? We have a good mental picture of what 1 atmosphere of pressure is, because that's what the world around us is like. So 1 atmosphere is equivalent to 1.013 times 10 to the 5th pascals, right? A pascal is 10 to the 5th, 1 bar is 10 to the 5th pascals, so an atmosphere is pretty close to a bar, but not exactly 1 bar. 1 atmosphere is about 1,000 millibars. Right, so if I look at this weather chart, this is measured in millibar, and I can see, most of the pressure is varying somewhere around 1 standard atmospheric pressure. 1 atmosphere is 14 pounds per square inch. Right, so you can think about that. 1 atmosphere means there's 14 pounds per every square inch of a surface. So if you look at the wall of your room, which is probably thousands of square inches, there's thousands of pounds of force affecting that wall, right? Just from the atmospheric pressure. 1 atmosphere is also 760 torr, or a torr is really close to millimeters of mercury, not exactly, so it's a slight variation there. So we have to make sure we understand all these different pressure units. We can also talk about how we measure pressure, and there's a lot of ways to do it. A lot of the time, one of the simplest pressure gauges is called a manometer. This is an example of a manometer, and in fact, some of you may be able to go into the basement of your house and actually look for one of these. If you have radon mitigation system, you may actually have a manometer in your basement. And okay, so this is a particular type of manometer, and a manometer works pretty simply. You have a tube that's U-shaped. If you have the same pressure in this opening and this opening, you should expect that water level to be relatively constant. But if at one opening you have a different pressure than the other opening, there's going to be a bigger force applied on this surface of the water. So you're going to have the water be at a different, it won't be level on either sides of the manometer. And based on that difference, this is 2 inches high or something like that, you can actually measure the pressure on the other side of the manometer. All right, so for a radon mitigation system, you may have this radioactive gas coming up from underneath your house. There's uranium in the rocks underneath houses. That uranium decays, sort of a bunch of decays into radon, another radioactive gas, which comes up under your house. And so you don't want that in your basement. So sometimes houses have radon mitigation systems where basically you want a lower pressure underneath your house so that the radon isn't going to come into your house. In fact, the air in your house, if anything, will get pushed under your house. So if you look here, on one side of the manometer is open to the atmosphere. The other side of the manometer is attached to this pipe, which goes inside this pipe here. Right? So this pipe goes under your house, and I can see that the water level on this side of the manometer is lower than over here. So there's higher pressure over here than there is inside this pipe, right? Which means the pressure in your house is higher than the pressure under your house, which means that if there was a hole in your basement or something, air from your house would get pressed down out under your house instead of radon under your house coming up into your house. So that's just a nice example of a pressure gauge. And there's many other types, but this is one you could build on your own. So that's it for this video.